All right, welcome back. Let's talk about probability. We're ready. We had to learn how to count to get here, right? So again, this is going to be a review of things that you've seen in a previous math class, but we're just going to hit it harder and talk about it through the lens of set theory, of course. So let's start with some silly examples that are about correlation and causation. Hopefully you've seen this phrase before. Correlation is not the same as causation. This is kind of a probability topic, so we might as well bring it up because you should know this. So here's a silly graph of, on the red axis, you got per capita cheese consumption. So people over time, for these years at least, seem to be consuming more cheese, which is, I guess, great news. I love cheese. And then we have a graph on the black side that is the number of people who died by becoming tangled in their bed sheets, and that is surprisingly in the hundreds. Do you see how both of these graphs are correlated? They're doing the same. They're both going up at about the same rate. So they're very highly correlated. And does that mean, though, that we should stop producing cheese because that will save these people from becoming tangled? I don't think so, right? They're correlated, but they're not. One's not causing the other, at least in theory, right? Hopefully that's true. I'm pretty confident that it is. So just because you see some graphs that are aligned does not mean that one thing caused the other thing, all right? So these are silly examples, but one day you're going to look at two things and think that, oh, these actually check out. Maybe these are causing each other, when in reality you have to take a step back, all right? So here's another silly example of this. We have the global average temperature over time is going up, just global warming, right? And these are years where they took the readings. And also, the number of pirates, sadly, in the world is going down. So there's an inverse proportional relationship between the global average temperature and the number of pirates. Do you see it? That's unfortunate. So maybe if we just have more pirates in the world, we'll solve global warming, right? Again, we have a correlation, but there's nothing that implies a causation. All right, so that's silly. Hopefully that makes sense to you. And yeah, now let's talk about probability in general. This slide is a pun because we have to talk about something first called events. All right, so there's a bunch of new terms that maybe you've heard before since you've learned about probability in the previous math class, but let's just hit them harder and talk about it in terms of set theory as well. So, okay. When you're talking about probability stuff, there's always the idea of an experiment. That's something that you're doing that results in a number of possible outcomes. All right, so for example, if you've got a coin and you're flipping the coin, right, it could either land on heads or tails. Those are your outcomes, and flipping the coin was the experiment, yeah? Heads or tails. And so we can talk about the set of every outcome, the set of all possible outcomes. We call that the sample space. So what could a coin land on? What's the sample space of flipping a coin? It's either the heads outcome or the tails outcome, yeah? And you can also think about subsets of the sample space, like things I'm betting on, things that I really want to have happen right now. Those are called events. All right, so I really would like the event of just heads showing up. It's always a subset of the sample space. Or think about this in terms of rolling a die as well. I would really like a 1 or a 6 to show up on my die, not the rest of the sample space. So things that you might want to bet on, things that you really care about happening, those can be called events. Those are just subsets. So it's just a piece of what might happen. All right. We could next talk about graphs. Those are probability distributions, talking about what are the odds of every individual thing happening for a fair coin at least, right? The probability of it should be 50-50, but you can graph this. A probability distribution is a function over your sample space. So it's a function from elements of the sample space to probabilities. And so 0% is 0, and then 100% is 1. And so both heads and tails, if you give this to if it's a fair coin, the probability distribution over heads and tails of your coin should be taking heads to 0.5 and also tails to 0.5. Does that make sense? But the sum of all the probabilities must add to 1. You can't have 200% chances. The sum of all the things need to add up to 1. Okay, so that's the idea. And so here's a probability distribution for a coin, a fair coin at least. So on this axis you have either it's heads or tails, and then on this axis you have the probability. All right, so it should both be 0.5. Does that make sense? So that's the distribution for a fair coin, and you're flipping it. It's 50-50, right? 50% chance it lands on heads, 50% chance it lands on tails, and that's it, right? That's all you get. The sum of all those probabilities must add up to 1. So there's a 100% chance it lands on heads or tails. There's a 0% chance it lands sideways or something, right? So that's it. And you can also talk about like the probability of an event happening. Like, all right, I really care about if I'm rolling a die. Let's think about rolling a die for a second. Here's my best drawing, artist's rendition of a die. Like I really want, there's a 1, there's a 2, there's a 3, right? I really want, I don't know, a 1 or a 6 to show up on my die. And you can talk about the probability of an event, right? That's just a subset. You just like sum up the individual probabilities. So like if you have an event that's a subset of your sample space, then the probability of that event occurring, which we can just write as the probability of E, the subset itself, you just sum them up. Sum up the individual probabilities of each piece of that event, okay? Just like equal to the probability of 1 happening plus the probability of 6 happening, all right? And so there's that. The probability of like rolling a fair die or flipping a coin is a uniform distribution because the probability is the same, right? It's fair. So the probability distribution where every outcome has the same probability is called a uniform distribution. And those are super nice because like you can figure out the probability of an individual thing happening very easily because it's like it's 1/2. There's 2 outcomes, right? 1/6 for a die, yeah. So like that is a uniform distribution as well. If it's like if you're rolling a fair die, you got what are your outcomes? 1, 2, 3, 4, 5, and 6, right? And they're all the same. They're all going to take 1/6, right? That's your probability. Probability is 1/6. I hope that makes sense to you. That those two things are too close together for me. So let me do that. There. Okay, I hope that's making some sense. So that's a uniform distribution. If you like buy a cheating die, a loaded die, maybe the probability distribution looks a bit more like this. It's loaded so that the 2 comes up a lot. Maybe a 6 or something like that. This is not a uniform distribution anymore. But they all have to add up to 1 though. All right, the sum must add up to 1. You can't have a 200% chance of things happening. So I think that's what I wanted to say. And yeah, same for this one. Like the probability of heads plus like this. We're going to show this, right? Probability of heads plus the probability of tails adds up to 1 equals 1. Okay, there's that. And so coins are a good example of a uniform distribution. And fair dice as well. Coins have a uniform distribution. Okay, so there's that. And yeah, uniform just means same probability. I think that is everything that I wanted to talk about. Yeah, that's pretty much it. All right, onwards. So yeah, let's continue talking about events. You can talk about combinations of things. So we say that 2 events are mutually exclusive if if those sets of them, they're just sets at that point, right? If they're disjoint sets. That's another name for like the sets are disjoint. So that's what mutually exclusive means. So like here's an event like I really want my die to land on 1, 2, or 3, and here's another event like I really want my die to land on 4, 5, or 6. You see how those are disjoint, so those are mutually exclusive events, not the same as things that share stuff. So like in general, the union of 2 probabilities, like the probability of 2 events, their union, is exactly that principle of inclusion-exclusion, because there might be some overlap. They might not be mutually exclusive, all right? So remember that, like you got 2 events. Those are just sets at the end of the day. They might share stuff. So the probability of a union of events is equal to the probability of both of them, but you might have double counted that middle bit. So you got to subtract the probability of their intersection. But if they are disjoint, there is no intersection, so that goes to probability 0. All right, so we're tying all this back to set theory, but you can do probability stuff with it now. So this would be 0 when they're disjoint. All right, so you can also talk about the complement of an event, like the probability that it doesn't happen. It's the complement. And we say E bar to mean that. So the probability of the complement of event E is just it all has to add up to 100%. So it's just 1 minus the probability of E itself. Does that kind of make sense? So like here's all the events of my, or here's the sample space, right, of my my die. Sample space is 1, 2, 3, 4, 5, 6, and let's say I really want it to land on one of these guys. So like that's my event E, 1, 2, 3, or 4. The probability, or just the idea of the complement of an event E bar, is just like everything that wasn't part of your event E. So like this, what's left is going to be your E bar. Does that make sense? And so naturally the probability is going to be 100% minus the probability of E itself. Okay? A good use case of the complement is this example called the birthday paradox. It's a fun one. It's a very standard example. It's very surprising as well. It's a good use of the complement. Like you can't solve this without using the complement. All right. So here's a very interesting thing. It's a paradox because it doesn't make sense, even though it is true. So here's the question: like, what is the probability that in a group of n people, at least 2 people have the same birthday? So like you get a group of n people, like 50 people or something. Like what is the probability that at least 2 people have a birthday in common? Okay, and surprisingly, if you have just 23 people, it's already 50% chance that 2 people have a birthday in common. It's really cool. It doesn't make sense, right? It's a paradox. Like why so few we have such a high chance? But it is true. So here is how you solve and understand this. So to figure out this kind of probability, it's easier to just figure out the probability that nobody shares a birthday. All right, that's a very easy probability. Let's solve for that, because then we can just take the complement of this idea, right? The complement of the event that nobody shares a birthday would be that like at least 2 people shared a birthday, maybe more. You see that? It's like if I find this probability, if I subtract it from 1, I have my answer. All right, so let's find this one. So here's how you do it. You come up with a bunch of events for like the possibilities of people not sharing birthdays. So like, all right, what does that mean? So I guess in a group of 1, what's the probability that 2 people don't share a birthday? Well, it's a 100% chance, right? 365 over 365 for sure. There's a 100% chance that you have a group of 1 people that no 2 people share a birthday, right? Because you don't have enough people to begin with. All right. And then, all right, what's the probability that a group of 2 people, that a group of 2 people don't share a birthday? Like person 2 has a birthday on a different day. That's another event, right? And you end up multiplying these. It's like, all right, now I have, what's the chance that the second person does not share the same birthday as the first person? Well, you have 364 days that person could have been born on. Does that make sense? Over 365. So that's the probability that the second person did not share a birthday with anybody else. And you just keep on doing that. Like the probability that the third person doesn't share a birthday. Like now you have 363 days to choose from for that person's birthday. Over 365, like that's the probability. And these are independent events. Like one person's birthday doesn't control another person's birthday. So there's not a big deal. It does not make us worry. So you can multiply these events. And you get down to like, if it's 23 people at least, it's like 365 minus 23 plus 1 over 365. And this would be, all this stuff multiplied together, the probability that no 2 people, nobody at all in a group of 23 people, for example, share a birthday. And if we just take 1 minus that, we have the probability that the probability that at least 2 people share a birthday. All right, I hope that's making sense. So if n is 23. We can solve for it that way. And I have an example in Racket for us. Oops, I'm in the wrong file. Birthday paradox. So here is a fun function in Racket. So birthday paradox, so I take n, you give it a number, and it's gonna, like, given that n, like I'd call it 23, like, let's first figure out the probability that everyone was born on a different day. And so that's this calculation, like all the way down to this, calculating these probabilities. It's like just ranging from 365 to 365 minus n plus 1. And yeah, here's like the probability is just like you multiply what you got by this new thing. It's just your I over 365 because it's working its way down there. And so we can calculate the probability of like everybody born on different days, and we take the complement of that to get the probability of the birthday paradox, like everyone was born, or the probability of at least 2 people being born on the same day. All right, so we take 1 minus what we calculated to solve for that. All right, so for a group of 23 people, what happens? And then let me comment this one out just to surprise you. Boop. So for 23 people, the probability of nobody sharing a birthday in a group of 23 people is almost close to 50. So 1 minus is a little over 50%, 51-ish percent of 51-ish percent chance that a group of 23 people share a birthday. Isn't that cool? It's very surprising. And then what if you get a size 50 group of people, like the size of this class? Ooh, there is a 97% chance that, like, in a group of 50 people, like in this class, that at least 2 people share a birthday. Is that not wild? The probability that nobody shares a birthday in a group of 50 people is like 3%. That's insane. That doesn't make sense. It's a paradox. But we've got the math to show that it works out. Isn't that so cool? That's very surprising. So that's why it's called a paradox, but we can solve it. We can understand it. All right? So here is a question for you. It's going to require some counting knowledge, but it has to do with probabilities. All right? So let's say that we've got n white socks and n black socks in a drawer, and every white sock has a unique design, every black sock has a unique design. So you can tell them apart. All right, let's say that 2 socks are selected at random from the drawer, and every way of selecting the 2 socks is equally likely. They're all shuffled around or something, and you have no control over what you pick out. It's perfectly random, and the order in which you select your socks does not matter. Here are my questions for you. Assuming these things, how many ways are there to select the 2 socks in total? Like, how many ways total can you grab 2 socks from your drawer if you've got n white and n black socks? So that's a counting question, right? And then how many ways are there of selecting the socks, how many ways of selecting the socks result in 2 socks of the same color being chosen? So what's the odds, or I guess how many ways, not the odds yet, not the probability yet, but how many ways can you get 2 socks of the same color out of your drawer if you grab 2, all right? And then finally, what is the probability? Now you can calculate using these counts, right? You can help calculate probabilities. Like, what's the probability that if you randomly pick 2 socks that they're the same color? So like you can use your answers to compute that, and try to simplify your expression if you can, so that like you can get rid of your A choose B, because you're gonna have to do that. That's a hint. All right. So see if you can figure that out. All right. Do you see it? So first of all, how many ways are there to select the 2 socks? It's just like you're taking 2 socks. The order in which you take them doesn't really matter, like as long as you just took those particular 2 socks out. So like how many socks total do you have to choose from? It's 2n, right? 2n socks to choose from, and you're picking 2 of them. So there's 2n, choose 2 ways to do it, right? Because the order in which you pick them doesn't matter. It's like I pick white sock number 42 and black sock number 43 or something. It doesn't matter that I drew this one first and that one second, as long as I got both of them. So that's what the choosing works out as, okay? And then, all right, what's the next one? How many ways of selecting the socks results in 2 socks of the same color being chosen? Well, how many ways are there? You can split this up into like, all right, maybe you selected 2 white socks, or you selected 2 black socks, right? And you got n white socks to choose from, and like you're choosing 2 of them, so there's that many ways of selecting 2 white socks, right? Plus same amount ways of selecting 2 black socks. Does that make sense? Because you got 2 of them. And so that's equal to 2 times n choose 2. If we want to simplify this, how could we? So like, what is n choose 2? It's equal to n times n minus 1 over 2, right? N minus 1, because it's over 2 factorial, so it's just over 2. And if we're multiplying that by 2, the 2 cancels, right? Those are going to cancel. And so that's equal to just n times n minus 1. I hope you see that. And now we can use these ideas to compute probabilities. Like, what's the probability that if you randomly choose a pair of socks that it's the same color? Well, it's how many ways you get, can you select 2 socks and you got the same color, over how many ways can you pick 2 socks in total. Does that make sense? So that's the secret there. So it's just like, it's this over this. Does that make sense? And so we want to simplify that if we can. It's going to be whatever this is, so n times n minus 1, over whatever this is, and so let's figure that out. Let's simplify that. So 2n choose 2 is going to be equal to, right? Start with 2n times 2n minus 1, and then it's over 2 factorial, so just over 2. That is a 2, by the way. That's not very legible. There we go. And so can we simplify that? Well, we can get rid of one of these 2's, right? There you go. That's n times 2n minus 1. And so that's what we're dividing by. So that's your total number of outcomes. And 2n minus 1. There we go. And then can we cancel some other things? Like those can cancel now. And so I think the most simplified form of this would be like n minus 1 over 2n minus 1. So those are your probabilities. It looks like it's just about 50%, assuming n is large. Does that make sense? That's not too bad, right? That is not too bad odds, and it kind of makes sense given that you have the same amount of each of those. That is helping us understand our intuition, maybe. So yeah, there's a good question, and then here's another good question for you to try. So you're going to calculate some probabilities, and it might help to write a program, by the way. So which is more likely? Let's say that you've got 2 dice, and you're going to roll. You're going to add up what you see on the dice after you roll them. So what's more likely? Rolling a total of 9 when you got 2 dice, or rolling a total of 9 when you got 3 dice? All right, so think about it. Think about it. Like first, figure out what is the sample space for each experiment. Like you're rolling 2 dice, right? Or you're rolling 3 dice. And what are the possible like things that you're going to get out, right? What are the possible sums of the dice, like either 2 or 3 that you're getting out? Like what are the events that we care about? Think about that as well. And then maybe writing a program will help you solve for the probabilities of each, all right? So that's my question for you. Give it a try. It's a good question. All right, so first of all, like what's the sample space for like rolling 2 dice? It's really, if you think about it at the end of the day, like you got, what are all the ways that you could roll like a 9 with 2 dice, first of all? You could, it's my best drawings of dice. You could roll like a 6, right? A 6, 1, 2, 3, 4, 5, 6, and then a 3. You got plenty of other options though, don't you? So think about those. But like, in terms of rolling 2 dice, what is your sample space? What does it look like? It's just a bunch of pairs, right? It's like what was the number on the first dice, on the first die, and what was the number on the second die? Like 1. The first one's a 1, the second one's a 1. That's an outcome. So like here's the sample space for rolling 2 dice. For examples, like the first one's a 1, the second one's a 1, the first one's a 1, the second one's a 2, all the way to like they're both 6s. Does that make sense? So it's just a Cartesian product. It's like this could be 1 to 6, this could be 1 to 6. You have all the options. So this set is equal to the Cartesian product of 1, 2, 3, 4, 5, 6 with itself, right? Cross itself. 1, 2, 3, 4, 5. Can I complete this in time? Kind of. Cool. There you go. Does that make sense? And then the same for like the sample space of rolling 3 dice. Like the sample space of rolling 3 dice is like, all right, either they're all 1s, you got 2 1s and a 2. It's like, it's 1, 2, 3, 4, 5, 6, just like to the 3rd power, right? It's a pair of, it's a tuple of 3 things. It's like the 3 dice could all land on 1, the first 2 could land on 1s, the second one could land on 2, all the way to like, they're all 6s, yeah? That's your sample space. Try to figure out, like, you can see how easy it is to figure out what the size of those are as well, right? And then like, what are the events that we care about? Yes? So now let's figure this out. Like, all right, rolling a 9 when you have 2 dice, what are the ways that you could do that? So like, this is event with 2 dice that I care about. Like, I guess you could roll a 3 and a 6. Like the first one's a 3, the second one's a 6. You could roll a 4 and a 5, right? First one's a 4, second one's a 5, or first one's a 5, second one's a 4, right? And then 6, 3, and I'm pretty sure those are the options. So you got 4 of them. And then for like, well, how many ways are there to roll a 9 with 3 dice? Then it gets a little more complicated because like the first one could have been a 1, then this one could be a 2 if that one's a 6, right? You have some weird options like 1, 3, 5, 1, 4, 4. And so there's like a bunch of more ways to do it, but you have more like options total. So like the question is which one wins out, all right? So to calculate probabilities, at least, we need the sizes of these things. Like, all right, it's just the size of this over the size of that. That's the probability of getting a 9 with 2 dice. Does that make sense? And then like the probability of getting a 9 with 3 dice is like the size of this over the size of that. So like for these, it's very easy to figure out what are the sample space sizes. The size of the sample space when you're rolling 2 dice is just like, all right, you have any number, 6 numbers possible here, 6 numbers possible here, so it's just 6 squared. Okay, so like it's 36, right? There's that, and then the size of s to the 3rd power is 6 cubed. Yes, I hope that makes sense. And so there's that, and then what else? Now we need to like, we know that the size of e2 at least, that one was easy. It's like e2 That's 4. But the size of E3, it's easier to just write a program, I think. And so I did that. I did that for us. Hopefully you did too. So here's this examples. Here I am rolling 3 dice. So I'm ranging I, j, and k from 1 to 6, and I'm seeing if ever I plus j plus k is equal to 9. And I'm printing out when that's true. Okay? And I'm printing out that count. Boop. And so it just so happens that here are all your options. There are exactly 25 of them, all the way starting from 126 to 621. In lexicographic order, isn't it? So there's that. And so that's 25. E3 is 25. And now I can do my math. So the probability of rolling 2 dice and getting a 9 is size of E2 over size of S2. That's something. Versus, right, the size of rolling 3 dice. What's the probability of rolling 3 dice and getting a 9? It's size of E3 over the size of S3, which is, this one is 4 over 36, and this one is 25 over 6 cubed, which I don't remember, but Python knows. Whee. And so that's 216. So which one wins? I still don't know. So 4 over 36, 11.1-ish%, and then 25 over 216. Ooh, 11.6-ish%. So it looks like 3 dice. 3 dice wins out. Even though you got more options, you still have just a little bit more. A little bit more probability, a little bit more chance. 3 dice is the answer. Does that make sense? That's so cool, I think. So yeah, like, I told you a bunch of stuff. Like, I defined a bunch of stuff, and now it's just like solve problems until you get it, I think is my strategy. So I have another question. Like, pause the video, please, try it. Try it, that's really gonna help. This is another one where you can write a program and it will help. So here's another example. Let's say that we're picking an integer randomly from the set 1 through 50, of all those numbers. What is the probability that your integer that you just randomly chose is divisible by either 3 or 7? Could be both too, doesn't matter. Either 3 or 7, all right? Logical or, inclusive or. So here is my hint for you. All right, so try it. My hint though is like, you can split it up into a bunch of different events. You've got like divisible by 3 event and divisible by 7 event, but you will also need to find their union, right? Your goal is to find the probability of the union of events, but you'll also need to, at the same time, find their intersection, because there is some overlap. There are some numbers that are divisible by both 3 and 7, right? Does that make sense? So those are my hints to you. You'll need to use that formula, all right, for their union, because they are not mutually exclusive. So I think a program would be a good one, but give that a try, all right? So, okay, what is the event of having a number out of 1 through 50 divisible by 3? Well, there are all these numbers, right? 3, 6, 9, 12, ... all the way to, I think, 48. That's the last number that's divisible by 3. And then what's E7? That's 7, 14, 21, 28, 35, 42, and 49, right? So what's the size of E3? If you think about it, I think I did a program for it. But writing a program helps. Here's that program. Here I am counting all the numbers that are divisible by 3, 7, and both. It's like you just do the modulus and check if the answer is 0. And I made it's called a macro in Racket. It's called inc with an exclamation point. It's going to increment a variable. It's like the x++ kind of thing. It's really cool that you can do that yourself. But all I'm doing is just ranging from 1 to 51 and checking, like, all right, for my current I value, is it divisible by both? If so, I will like keep track of that. Like, okay, add 1 to it was divisible by both. And then also, because it was divisible by both, like add 1 to my individual counts as well. Like, all right, if this number is divisible by both, then for sure it's divisible by just 3 and also just 7. Otherwise, if it was just by 1, divisible by just the 3, increment that variable. Divisible by just the 7, increment just that variable. And then I'll have my counts at the end. And so it looks like there are 16 numbers that are divisible by 3. That's the size of E3, 16. And there are how many numbers that are divisible by just 7, divisible by 7. 7 of them, surprisingly, that's cool. 7 of them, and there are, though, 2 ones that are divisible by both. Can you see them? It's going to be 21 and 42. You see them? So those will also be here, 21 and 42. Those will be shared by the two of them. And so what we're trying to do, right, is to calculate the probability of E3 union E7, those two events, and that's equal to, if we follow our formula, probability of them individually minus their intersection probability. E3 intersect E7, and the size of their intersection we know to be 2 now. You see it? So writing a program really helps here. And so what are these odds? So we got the total number is 50, right? Probability of E3 just happening, and that's 16 over 50. Yeah. So it's 16 over 50 plus E7 is 7 over 50 minus 2 over 50. Yeah. And whatever that is, that's 16 plus 7 is what? 23 minus 2 is 21. So it's 21 over 50. Those are our odds. So it's a little under 50%. Yeah? Interesting. So that's like not bad odds, honestly. It's better than we thought, maybe. But now we know how to solve for it. All right. So yeah, a few more things to talk about today. The next main one is called conditional probability. This is a very, very important thing. You can get very far with this idea, all right? So sometimes you know that like we look at like the results of like our experiment. We notice that event F happened. We know that for sure, but if we know that that happened, sometimes we can use that fact. Like when I know that event F happened, you can use that fact to figure out how likely it was that E also happened, assuming you didn't know that already. It's very interesting. Like if you know that one thing happened, it may influence some other event. That's what we're trying to say. That's called a conditional probability. All right. So let's see here. What is the best way to show that? So like here is event E. I don't know. Let's say that there's event E. Here are a bunch of outcomes, right? A bunch of outcomes. A bunch of outcomes outside of that as well. And then there's also an event F. All right, event F. So here's event F, and they share some. See it? So if you know that event E occurred, do you see how that might help you notice if event F occurred? Like if there's a bunch of stuff out here, maybe it's very unlikely usually for F to occur. But if you know that E occurred, what's the probability that F occurred? It's not like it's easier to solve, right? The probability that F is like this over like the entire sample space for just calculating the probability of F. But if I know that E happened, right? If I know that E happened, how do you calculate that probability now? Well, what's the probability, if I know that F happened, excuse me. If I know that F happened, what's the probability of E happening? That's my goal right now. Well, if I know that F happened, what's the probability of E happening? Well, it's this guy, right? Because I know that like I'm within F here, right? It's the probability of like count all these up over all this stuff. Because I know that F must have happened. Like the probability of E happening, if I knew that F happened, is this guy over that count. Do you see how that's easier to solve than like E over everything? That may be small, but if I know that F happened, it may be easier to solve. So sorry, I got it backwards when I first explained it. We're talking about if we know that F happened, what happened with E. All right, so I hope that makes some sense. You can do it the other way as well. And that's called a conditional probability. It's like E given F. Given that F occurred, what's the probability of E? All right, and this is the way you write that. It's probability of E, then a little bar you read as given, and then F. Probability of E given F. All right, it's a conditional probability. E occurring when I know that F occurred, it's this, right? Probability of E given F is the probability of their intersection, this guy, over the probability of F, because I know that that happened. Do you see it? That's how that works, okay? So yeah, here, that's a good idea. And let's see here. Let's do this example. What's the probability of, like, here's another one. Then we'll get into independence as well. So the probability of, I don't know why, but I did this in a different color last time, might as well. Probability of E given F in this example here, this one is easy to calculate. So it's equal to, what is the probability of their intersection, which is 2 over, right? Oops. What was the probability of E given F? Is the probability of their intersection divided by the probability of F. Does that kind of make sense? So it's like, it's 2 over 1, 2, 3, 4, 5, 6. Do you see that? That's how you can calculate that. 2 over 6, which is simplifying to 1. That simplifies to 1/3. So it's like the probability of their intersection over the probability of that thing, because we know that F occurred. And that might be different than the normal probability of E by itself. Does that kind of make sense? That could be different, but sometimes it's the same. Sometimes knowing that F happened doesn't change doesn't change the odds of E happening. So they don't influence each other. And when they don't influence each other, we call them independent events. So two events are independent if conditioning on one does not change the probability of the other. It's like there was no influence. We gain no knowledge by knowing that F occurred. So that's what that means. And so here are 4 bullets that are exactly the same ideas. They mean exactly the same things. All right, they're equivalent statements. And here are some cool things to know. All right, that they're equivalent. You can prove that 2 events are independent with any of these ideas. So like, all right, E and F are independent. That's one thing. That's equivalent to this. It's equivalent to the probability of E given F to be exactly the same as the probability of E. Like conditioning on F gave us no new knowledge. They were independent. Does that make sense? Same with the flip side. If the probability of F given E is the same as just the probability of F, conditioning on E gave us no knowledge. And so that means that they were independent. All right. One did not influence the other. And you can use these two to also come up with this rule. The probability of their intersection is the same as the probability of multiplying them together. That is only true if they're independent. If that is true, that means they're independent. Does that make sense? And you can figure that out by like solving for this idea. Like if this is equal to that, and like you can like get them on the right side. There's a way to do it, I promise. All right. Let's see. What do I want to do with that though? Let's see here. Dun, dun, dun. Yeah, because you can just like here, you can just like multiply that, bring it over to that side. That's how you could solve for this equation, if you know that's true. So these, E and F, I've constructed just so brilliantly to make them independent. All right, so I claim that these 2 events are independent. So the probability of E given F is going to be exactly the same as just the probability of E. That's one way to notice that they're independent. So here, the probability of E by itself is 3 over the whole thing. 3 over what? 1, 2, 3, 4, 5, 6, 7, 8, 9. 3 over 9. It is 1/3. That's the same as the probability of E given F. So knowing that F occurred gave us no extra knowledge of whether E occurred. Do you see that? They're independent events. All right, and the same is true for the other way. If it's true for one way, it's automatically true for the other way. Those are all equivalent statements. So the conditioning on E gives us no knowledge about F. So the probability of F given E is the same as the probability of F. So what's the probability of just F? That's equal to 1, 2, 3, 4, 5, 6 over 9. That's 2/3. And that, I claim, is the same as this. Probability of F given E. What is that? Dun, dun, dun. That is, if I know that E occurred, there's that. So it's like 2 over 3. See that? See that working like that? So yeah, that's how that works. What is a good way to show that? So we already did E given F. We did F given E. So just like in general, E given F is like probability of these guys, their intersection, over the probability of the whole thing. That's how we calculated that. That's the 2 over 6. Okay? I hope you see that. Let's see what else. And yeah, this one also checks out. Just the probability of E intersect F is the same as you multiply them together. So like, what is the probability of E intersect F here in this example? Well, there is a way. It's going to end up being the same as those multiplied together. Well, let's confirm that. It's going to be E intersect F is 2 over the whole 9, right? 2 over 9. And that's the same as 2/3 times 1/3. Isn't that cool? I love it. Let's see, what else can I show you here? Dun, dun, dun. So in general, like if you didn't want to do this kind of counting, like that's the quick way to do it for the probability of E given F, you could also calculate it just like exactly this. The probability of, that's another way to get at it. E given F is the same as probability of their intersection, which we know to be 2/9 over the probability of F occurring, which is 2/3. 2/3, which is equal to what these, you like cross multiply, right? So it's 6 over 18, which is 1/3. That's another way to get at it. All right, so you have options. Hopefully you see both ways, and that is conditional probability. Sometimes knowing that one thing occurred, knowing that F occurred, gives you some new knowledge, like you know that E was very likely or less likely, depending on that. Isn't that cool? So yeah, here's a fun example of like maybe not so much conditional probability. Actually, yes, it is an example of conditional probability, but it's going to show some fun ideas about like intersections as well. So this is a fun example that like everybody likes to show. It's like an old game show. I'm honestly not sure if it was real or not, if it was made up just for probability lectures, but let's pretend that it was a real game show. I think it was in the UK at least, that was supposed to be. It's called the Monty Hall Problem, or there was apparently a game show called Monty Hall something, all right? So here's the game, all right? So there are 3 doors on this game show, all right? 3 doors. They're labeled 1, 2, or 3, and there are, here, let's pretend that they're all closed right now. Here are your 3 doors. You got numbers on them. There's 1 car, all right? You can win a car in this game show. Like, so there's a car behind one of the doors. All right, so here's your car. Behind the other 2 doors is a goat. All right, so I have 2 goats, and apparently they're being quiet, so you can't tell which door they're behind. So there's a car behind one door and 2 other goats behind the other doors, and you get to like immediately you can pick which door. Like you can say, I think that the goat. I think that the car is behind door 2. Like that's your guess. You can make a guess in the game show. And then the host, Monty Hall, will open up one of the other doors. He'll open up a door and show you that there's a goat behind the door. He'll always open up the other door with a goat in it, assuming you guessed the one with a goat already. But if you guessed one with a car, he'll just randomly pick one of the other 2 doors to open. Does that make sense? So he's going to show you a goat behind one of the doors that you did not pick. All right, so he'll open up one of the doors for you and then ask you, do you want to switch your guess from door 2 to door 1, which is the other one that's still not open? Do you want to switch your guess right now and open up door 1, or do you want to remain with your guess of door 2? All right? That is the question. That's the game show. And so, like, is it better, probabilistically, is it better to swap, always swap to the other door, or keep your original guess? All right? That's the question. And this is very counterintuitive. It's another paradox, kind of. It just so happens that if you switch, it's always better. It's always better to switch. All right, let me kind of prove that to you, just in a hand wavy way. We can simulate it in Racket. All right, so it's kind of like the probability of like, should I stay given I guessed the car correctly or given that I didn't? Like you can think about this in terms of conditional probabilities, but we won't go there. So here's kind of the trick. The probability that if you stayed, like you kept your guess and you got the car right, that probability is 1/3. Because if you think about it, right, it's just the probability that you got the car on the first guess. Does that make sense? Like if you stayed, like you're banking on the probability that you got the car on the very first round. The door opening doesn't really give you any new knowledge. Does that make sense? So like, what's the probability that you guessed the car right? Because he's always going to open up a door with a goat, even if you got it right or not. That's just 1/3. You have a 1/3 chance of guessing the door right the very first time. Does that make sense? Stay and you get the car. All right. The probability that you switched, if you end up switching and you got the car, is going to be the other one. It's going to be 2/3. These are disjoint. They add up to the whole thing. All right, so that's kind of the idea. And let me try to prove that to you. Let's say you guessed door 2. And Monty Python is always going, not Monty Python, Monty Hall is always going to open up a door with a goat. Like you're going to see a door with a goat. And then the question is like, do I go to this door or not? What are the odds that it's behind, like, a door that you did not guess? That's how you solve for this. What are the odds that the car was behind a door that you did not guess? 2/3. Does that make sense? And so the odds that you got it wrong first are pretty good, right? They're pretty good. So you should always switch, because he's going to open one of the doors with the goat. So the other door now suddenly has the 2/3 chance of it being right, because this one is like, it cancels it all out. Does that make sense? Like, the odds that you didn't get it right the first time is a 2/3 chance, right? And so he opens up a door with a goat. You should always switch to the other door, because there's that just forces the 2/3 chance of that car to be right there. Does that make sense to you? You're always better off going with not your gut, but always switching. Does that make sense? It's very unintuitive. But that's why we're learning all this. You can formulate this in terms of conditional probabilities, but it's kind of like an intersection almost. These are the same, right? It's just like one is the other. They're split off, perfectly split off. And so here's a simulation. Like, if you don't believe me, here's a simulation in Racket. We're gonna play the Monty Hall game 1 million times, and we'll keep track of how many times we won if we stayed, how many times we won if we switched to the other door. And so here's a function that just like runs a simulation. I'm gonna call that in a loop a bunch of times. So I'm gonna run it that many times and keep track of my wins. All right. And so we'll also, because we know how many times like we're running our simulation, we can do a probability calculation as well. Like how many times we won over the total runs. Okay, so here it is. Here's how you do it. It's like, all right, let's pick a random number from 1 to 3 to like be the door that really had the car in it. And then we'll randomly pick, let's pretend randomly, we're going to pick the door that we want at the very beginning. And so we'll keep track of if we won by staying, by like, was the door that we picked equal to that initial door that contained the car? All right, so we'll add 1 to our count then. Otherwise, we'll like randomly pick a door to reveal, and like we're simulating it, right? And like figuring out which door we can change to by using filter. It's very cool. Like, here's the door you're allowed to go and switch to, and if you switch to it, what are the odds that you won? All right, so like if we change to that door, was that the one with the car? What are the odds? What's the chance? If it checked out randomly for this simulation, we'll add 1 to our count. All right, so that's the idea, and yeah, I think that's everything. I think that is what I wanted, and yeah, we zero out everything at the very beginning and give it a try. So we're running this simulation 1 million times. And then here it is. It's about 33%, see it, 33.3% that you won by staying with the same pick that you got. And then there's a 66.7-ish% chance. Exactly right. It's almost perfect, right? Very 2/3 probability that if you switched to the other door that you won the game. Isn't that so cool? That's a fun example, I think. And yeah, that wasn't a good enough example of conditional probability. So here's some questions on that for you. So here's a big long set of questions for you. Please try them all, and we'll come back and discuss. But let me explain them first. So okay, let's say that we've got a bunch of letters, like on a piece of paper, like on a bunch of different pieces of paper. We've got the following letters, A through G, and they're put into a random order. So they're shuffled. All right, they're permuted. All right, so every permutation is equally likely. All right, so maybe, I don't know, this was one of your shufflings. Like this is the random order that you got these letters in. A, D, C, B, G, F, E. All right, some ordering of them. It's just a permutation, right? Here are some events. Event A. Event A was the letter B is exactly in the middle of your permutation. There's exactly three letters on the left and 3 letters on the right of it. So there's your B right in the middle. All right, so that's event A. What are the odds of that happening? Right, there's a bunch of different options, right, of the B falling in the middle, and these other ones are jumbled. So those are events. That's one event. Event B is that the letter C appears to the right of B. It doesn't have to be immediately to the right; it just has to be somewhere to the right of it. All right. So like this one would be following in that event. So like here's C, and then here's B. C is to the right of B. It's not. It doesn't have to be immediately to the right, but it has to be somewhere on the right side of it. Does that make sense? There's C somewhere to the right of B. Doesn't have to be right next to it, but it could be. That's event B. And then here's event C. the letters D, E, and F occur exactly in that order anywhere within the permutation. Like they could be here, could be at the start, could be at the end, anywhere is fine. All right, so those are your events. And now try to figure out what are your probabilities, right? Calculate the probability of each of these events, A happening, B happening, C happening, okay? And then also some conditional probabilities. So you'll have to come back to this slide and think about like all right, you're gonna have to do some intersection calculations, right? So think about that. And so like, what's the probability of A given C? All right, given that you know that D, E, F occur in that order, what's the probability of B being in the middle? What's the probability of A given B, given that you know that C is somewhere to the right of B? What's the chance that B fell in the middle? And then with that, that will tell you if like A and B are independent events or A and C are independent events. Tell me if they are. All right? That's my question for you. All right, do you see them? Do you see? Did you get it? This is a harder question. It's a long question, but it's a good one to practice with. So like event B, remember, just like somewhere C is after B. It doesn't have to be very close, but like those are allowed, but like C being anywhere to the left of a B is not part of that event, okay? And so there's that one. And then, yeah, when you're solving this, the hint for event C is like D, E, F occur in that exact order. So like when you're trying to like figure out how often would that occur, just kind of like treat D, E, F as one big character because it can't move, right? You have to be exactly like that as a big chunk. So yeah, those are some hints and some ideas, but let's do these calculations. What is the first one? Is like, what's the probability of each of these events? Probability of A, for example. All right, probability of A. What are the odds that B is right in the middle? All right, what are the odds that B is right in the middle? Let's think about this. All right, so it's going to be all the ways that B could fall in the middle over all the ways total to jumble these letters. So first of all, how many ways are there to jumble those letters? There's 7 letters, right? And so it's going to be 7 factorial ways to jumble all those letters. And if you force that B goes in the middle, do you see how you have 6 more choices to actually make? So that's going to lead into the right answer. All right, there. If you have fixed B to be in the middle, like you've put it there, how many ways are there to jumble the rest of the letters and have B in the middle? There's 6 factorial ways. Do you see that? So that's how many ways that B could be in the middle. Does that kind of make sense? Those are like 6 factorial are all the ways, like that's the count of the number of ways that you could jumble the 7 letters where B is in the middle, because like you fix the B and now you have like 6 more things to choose from, 6 more things to range around, 6 more letters to jumble. Does that kind of make sense? So yeah, that would be 6 factorial over 7 factorial. That's the count. That's the number of ways that B could remain in the middle and you jumble the rest of the characters over how many ways are there total to jumble all the characters. All right, so that's the probability of A. The probability of B, what are the odds that C appears to the right of B? It doesn't have to be necessarily right to the right of it, but somewhere to the right of it. If you think about it, if you think about this, it's just as likely, right? It's just as likely that if you randomly jumble your letters that B's to the left of C as to being on the right of C. Does that make sense to you? Like if you stare at the problem long enough and you think about it, like in a random jumbling, like you have no control over B versus C, right? There should be just as many where C's to the right of B as many as there is to the left. Do you see that? So it's just going to be 50-50, 0.5%. Or not 0.5%, but 50%, 0.5 probability that event B occurs for a random jumbling of those letters, of those 7 letters. Does that make sense? I hope it does. And then finally, event C, this is still part A only. What are the odds that that DEF occurs in exactly that order? Okay, DEF occurs in exactly that order, and so it's like you fixed D, E, and F as one big character, and you can jumble like A, B, C, and G now. You really have like four characters left, and like DF is one big character, right? So it's like there's only 5 real characters. There's A, B, C, there's G, and then DF is just one big chunk that moves around by itself. So there's really 5 characters to move. So if you think about it, what are all the ways that those could appear with DEF right next to each other? Like you fix the DEF somewhere, and then you like consider it one to be one character, right? And so it's really five factorial, right? 5 characters secretly to jumble now, because DEF is one big character. There's like 5 real characters, and you're jumbling them. That's how many ways there are to jumble them, and then that's 7 factorial total to do them all, yeah? So there's that. And I hope this is kind of making a little bit of sense. This is a harder question. I'm doing my best to give you some intuition, so please yell at me if you have any questions about this stuff. I don't know why I circled that. Let me undo that. And now we're ready for the others. All right, so let's do some conditional probabilities. What's the probability of A given that C occurred? All right, so let's think about this. We can do the formula, right? A given C is the probability of the intersection, A intersects C, over the probability of just C. So this is part B now. The probability of A given C occurred is the probability of their intersection, intersect C, over the probability of C, which we know already. So this is the new thing to calculate. That's going to be something over the probability of C. All right, so let's try to figure this out. What's the probability of A and C occurring? So the letter B is in the middle, and then also D and F occur together. Let's think about this. So, okay, what are all the ways that this could happen, right? So if we've got 7 letters to jumble, yeah? 5, 6, 7. 1, 2, 3, 4, 5. Did I do this wrong? Yeah, I did. Give me a second. That's 5, 6, 7. There we go. So, all right, if we want B to be in the middle, and then also D and F occur in order, right? That one and this one. So B is in the middle, and then D, F occur in order. Do you see how, like, D and F can only go over here, or, if B is in the middle still, over here? Like, you forced where D and F can go. They can only go on this side or this side. And so, really, this turns into a question of, like, how can you jumble? Like, you forced these positions on B, D, and F. You're either there or there, and then you have the remainder of your 3 characters left to fill. Does that make sense? So it's really, like, either you're here and you have 3 characters to jumble, or you're here and you have 3 characters to jumble. You can count all the ways now very easily. It's like, all right, with 3 characters left to jumble and everything else looks like this, how many ways are there that look like this? 3 factorial ways, right? And then same with this one, like you force B, D, and F to be right there, like you've made those choices. What are the other options? Like how many ways that look like this are there? With 3 characters left to jumble, that's another 3 factorial. Does that make sense? And then the probability of like this occurring, A intersects C, is like those ways over the total ways, 7 factorial. Does that make sense? So that's the probability of A given C. Or sorry, not A given C yet, but A intersects C. So that's the probability of, like, that's the counts of all the ways of those things happening together over the total ways total to jumble all the letters. That's your probability, and we're dividing that by the probability of C, okay? Whatever that is the answer. We can calculate that later, okay? But that's how you can kind of come up with that. You see it? It's kind of cool. And then next is the probability of A given B. That's for part C. Probability of A given B. This will take some more thought. Again, it's the probability of their intersection. A intersect B over the probability of just B occurring, which we already know. All right, so again, it's going to be equal to something over the probability of B, which we have already. All right, so what are those 2 things that we want together? So again, B is in the middle, and now C appears to the right of B somewhere. Doesn't have to be right next to it, but it has to be somewhere to the right of it. All right, does that make sense? So, if you think about it, 10, 10, 10, what are all the ways to have the, like, 1, 2, 3, 4, 5, 6, 7, you're filling in all these letters, right, at the same time. Like, count all the ways for this to happen together. B's in the middle, and then C is to the right of B. So, what are all the ways to put B in the middle? There's only one way to do that, right? So 1, let's start our counts, right? And then you better put C in one of these spots, right? You have 3 spots to place your C. Does that make sense? It's got to be somewhere to the right. In one of those 3 spots. So there's 3 spots. You place the C, right? Put it somewhere. And then, like, you had 3 options. And now you suddenly have 1, 2, 3, 4, 5 slots left to fill, right? You can jumble the rest of your 5 letters in those 5 slots. So you have 5 factorial ways to do the rest. Does that make sense? That's how you can solve for that, okay? You forced the C somewhere to the right of B. You had 3 options to place it. Only one way to put B in the middle. And then over the probability of A intersect B is like all the ways, count the ways to do it, over counting the ways to jumble all the letters in total, which is still 7 factorial. So there's your answer. All right, so it's just 3 times 5 factorial over 7 factorial. Does that make sense? That's how you can solve for that. And that this calculation goes with this drawing. I hope you see that. It's kind of cool to think about it, right? And so now, finally, for D, we can calculate, like, all right, are these independent events? Like A and B, are those independent events from each other? And then same with A and C, are those independent events, or are they not independent? And the way that we can figure that out is based on these conditional probabilities. Like, all right, we calculated probability of A given B. Is that just equal to the probability of A? If so, they are independent, A and B. Does that make sense? Same with A and C, like probability of A given C. Is that just the same as the probability of A? If it is, then they were independent. All right. So let's look at that. So we did the A given C first, like probability of A given C. We want to compare that to the probability of just A. Is that equal? Question mark. And then same with the probability of A given B. Are those equal? Question mark. If they are equal, they're independent. If they're not equal, they're not independent. Okay, so let's do our calculations now. All right, what do we got? Let's go to Python. Let's do, does the math library have a factorial? Yes, thank goodness. All right, so we're safe. All right, what I want to do is, all right, the probability of A given C, let's just, I don't know, probability of A, let's save all these. That's math.factorial of 6 over math.factorial of 7. That's probability of A, probability of B is 0.5, probability of C is almost the same. So here, probability of C is 5 factorial over 7 factorial. And then, all right, the probability of A given C, or I guess we can just calculate this. The probability of their intersection, A intersect C, let's save that as well. Probability of A and C is equal to this guy, 3 factorial plus 3 factorial. Math dot factorial of 3 times 2, I guess, over math dot factorial of 7. That is the probability of A and C, and then the probability of A and B, which we need for the A given B calculation. Probability of A and B is this guy. So that is A and B is equal to the math factorial of 5 times 3. I'm trying to keep these as similar as I can to save myself some typing, over 7 factorial. So there's probability of A and B, and now we can do our calculations. All right, the probability of A given C. A given C is equal to the probability of A and C, which we've just calculated, right? Over, it's this guy, over the probability of just C. So over the probability of just C. Does that make sense? That's my A given C probability. And let's see, it's apparently, ooh, pretty much 10%, nice. Is that the same as the probability of just A? It is not. So they're not equal. All right, what does that mean for us? These are not equal. So that means they're not independent. Knowing that C occurred does give us more information about knowing whether A occurred. They're not independent. So one does influence the other. Cool, that's pretty nice. And then for this one, A given B compared with the probability of just B. If they're the same, they're independent. All right, what's the probability of A given B? It's the probability of their intersection, probability of A and B, over just the probability of B, which is 14.28-ish. And is that equal to the probability of A? Sorry, this was supposed to be, again, compare it to just A. My bad. And it is the same, isn't it? Well, look at them. Did conditioning on B tell us nothing about A intersect A and B together? Conditioning on B tell us nothing about A? Yes, it did not. Look at it. Exactly the same. So they are equal. So that means they are independent events. If you know that B occurred, you gain no knowledge about whether A occurred. Same probability. Those are independent events. And that is a very long, fancy question, but it gets at the heart of conditional probabilities, and I hope that that helps you as you study. So please come back to this question, try it yourself if you didn't already. Make sure you got it down and that you understand it, and ask me all the questions you need to until you get it. All right, but I think that's where I want to stop for the day. we learned a lot of cool new things about probability, some stuff that maybe you didn't know before. But yeah, now you're getting there, you're on your way, and I will see you in the next one.